Hello, I'm Umnik. Today I will be solving a regular contest and I will try to explain what I'm doing along the way. In problem A, we are given an array. We need to choose some value from this array and erase all the occurrences of this value, and we want to get lexigraphically smallest sequence after that. When we want something to be lexigraphically smallest, means that we want to minimize the first element, then the second, and third, and so on. How to minimize the first element? Well, what can be the first element? It is either the first element in the initial sequence, or we have to delete all the occurrences of the first element, and we just get the get something, and well, the first element will be the first element in the initial sequence, which is not equal to the first element. We can compare them, and if after the deletion the element becomes smaller, then this is the way to do it. Otherwise, we can't delete the first element, and we have to proceed in the same way further. So the solution is kind of like we're going left to right. If we encounter some element that it is its first occurrence, we can decide to delete all of them, and then we just find the next element which is not equal to it, using just linear search, I guess, and compare them. If the next element is smaller, then we have to delete this one. If we encounter the element which is not the first occurrence, then we can't make any choices because we had to make the choice to delete this element before. If we have already seen this element, then we do nothing, otherwise we mark it as seen and try to delete it. I could make some kind of two pointers, but just writing two nested loops works in linear time, because I will traverse each element only twice. So I'm skipping all the elements that are equal to this one. If I have reached the end, then it's good to erase my current element. Or if the next element is smaller than this one, then I call print answer from AI, which means to print all the elements which are not equal to this one. Otherwise I do nothing, just continue. And like I shouldn't be here. It's always good to erase the maximum element in the sequence. In problem B, we are given two permutations. And we want to find like some extension of longest common subsequence. Instead of it being common, they should have the, like, we should extract two subsequences from each permutation, and each element in from the second subsequence should be a multiple of the each element in the first subsequence. Problem A is accepted. When something should be a multiple of something, it's tempting to say like we have n-log n pairs of elements we can match and then do something. I guess that gives n-log squared with some segment tree, but I don't want to write segment tree for problem B. Well, 5 seconds, I guess that's the way. So we will be calculating dp from two positions. What is the longest, the most elements we can extract if the last two elements we take like this one and this one. On the second sequence we will, or on the first, it doesn't matter much. Yeah, on the first is easier because it's easier to iterate over all the multiples, but it doesn't matter much again. So we will iterate left to right, and for and we will store like dp values for each of these positions in segment tree, and when we are going to the next element we will iterate over all the elements that are multiplies of it and try to make transitions, like take these two elements as the next. Since we have iterated only elements that are to the left in P, we only care that the last one in Q should be also to the left, so we take maximum of dp values on prefix, which can be done with segment tree. So I need a segment tree on max with set in point. Like it should be max equal in point, but that doesn't matter much. Is that I'm making this mistake a lot recently. N should be a power of 2 for the way I'm writing segment tree. Come on. So what do I need? Need for element where it is in the second permutation, build. So element X is in position I. Now I'm going left to right through the first permutation, trying all the multiples of this element up to n. So these two cycles work in n log n. And now, yeah, I need to be accurate not to use the same element two times. Like if there are two or more multiples that are left to right, I would like if I just make an update here, I would be able to take like is element and then like this element in second permutation and then is element again and some bigger element in the second permutation. I don't want that. So I will write down all the positions in this array, sort them. It doesn't break the complexity because I have segment tree anyways. And I need to make transitions in reverse order. In problem C, we want to fill the matrix H times V with values from 0 to k minus 1, and for each row and column we are given the sum modulo k of the elements. We want to place some values, and we want to determine if it's possible, and if it's possible, find the maximum possible sum, not modulo k, just sum of the elements, which should be from 0 to k minus 1. Surely it's impossible if, like, we can calculate the sum of all elements in the matrix modulo k, either by rows or by columns, so the sum of all a's modulo k should be equal to the sum of all b's modulo k. If it isn't true, then it's impossible for sure, and like I'm guessing that it's always possible in all the other cases. But how to maximize the sum? we can fill all these cells with k minus 1, then uniquely determine what the values should be here, here, and then here. Like it maximizes the sum in all these columns, like except the last one, in all the rows except the last one, because well, basically in each row we will have some numbers that should give the given reminder modulo k, so it's this reminder plus k times something, and all the values are at most k minus 1. So basically we want to maximize the number of times we go over k, like we have to subtract k, but maximizing the sum in all the rows but one doesn't sound like a great idea. I guess instead we should do something like we should maximize the sum in all the either columns or rows, depending on which ones we have more. Like, let's say that we will in this picture I want to maximize the sum in all the columns, and I will fill all the cells except this. So in all of these cells I will place k minus 1. No, wait, this is bad. Now all of these values are uniquely determined, and like I haven't used the values in rows in any way. Yeah, that's bad. it feels like just making the finding the maximum possible value in each column independently, in each row independently, then sum over all columns, sum over all rows, and take minimum of them maybe is the answer. But I have no idea how to prove that. Like, if we place k minus 1 in all these cells, how do we maximize, like, we have maximized the sum in all the columns but all the rows but the last one. How do we maximize it in the last row? Well, we can put the values which has to be here in this cells, and then we can try to increase them by decreasing some of the values here, and we want to do that without going over k here. And also we shouldn't break any rows. And it feels like if the maximum for rows is bigger, then we can break something and everything should be fine. I don't know, I don't like this problem. Let's just submit this stupid greedy and see if it works. So the max value possible is put k minus 1 everywhere. Everywhere is m times. But it should be equal to x modulo k, which means that if it is bigger than x for now, then just decrease it until it is exactly x, which means take out current modulo value and then add x. If it is already smaller than x, then take out current value, take out k because we have to go through k, and then add x. Then do the same for b. well, I don't want to return to this problem anyway. Well, it's correct. I don't know why. In problem D, we have to find the number of segments of integers between L and R such that XOR of all integers in the segment is equal to V, where V is the given value. Let's say that XOR on segment is XOR of two prefix XORs, and it is well known that prefix XOR of all numbers from 1 to n is determined basically by n modulo 4. Let's write down some values. Zero 1 3 0 4 1 7 0. So XOR of every four consecutive numbers, like first of them, first of which is divisible by 4 is 0, because they have all the bits starting from the second equal, so XOR of them will be 0, and in smallest two bits they have 0 1 2 3, XOR of which is 0. So yeah, we will have zeros when n modulo 4 is 3. So let's look at n modulo 4. It can be 0 1 2 and 3. If it's 3, then result is 0. Then we can, from this 3 that before this, we can go here. So like from the 0, we will XOR it with new n, so here result is n. Then we will XOR it with n plus 1, which is n XOR 1, so it's n XOR 1, which is 1. Then we'll XOR it with this value, which is n, which was divisible by 4, XOR 2 and XOR 1, so it's n XOR 3, but that means that it's n XOR 1, or like n plus 1, and then 0. So we are looking at some segments. So this, let's call it some p of n for prefix. So it's prefix XOR up to n inclusive. So this thing is equal to prefix XOR of l minus 1 XOR prefix XOR of r. And we want it to be equal to v. Let's iterate over all possibilities for L and R modulo 4. Then we know L minus 1 and R modulo 4. What cases are easy? well, yes, when some, at least one of them is constant, like 0 or 1, it should be easy, right? Like if it's 0, then this should be just v, and depending on v, if it's 0, then L should be 4 modulo, should be 0 modulo n, so that L minus 1 is 3 modulo 4. If it's 1, then L should be 2 modulo 4. Otherwise, we just check that like each of these values can appear only once, so we just check for them. The same with 1, the same when this is 0 or 1, and when none of them is like this, it means that it is either n if it is divisible by 4, or it's n plus 1 if it is 2 modulo 4. So we can look at last 2 bits. It should be either 0 or 3 for v. If it's 0, then both should be of the same type. If it's 3, then they should be of different types. And then it's not clear. I guess it should be easier to like just choose these numbers and also don't care that this one should be smaller than this one. Let's just say that we are choosing 2 numbers from big L minus 1 to R and taking prefix source in them and taking them their XOR. We will calculate each valid pair twice. And also, if v is 0, we will calculate pairs when they're equal, but it's easy, like every such pair is okay for us, and it's easy to calculate this number. It's just R minus L plus 1. But what to do next? We can also trim our segment so that it's aligned by force. Just solving some numbers fixed by hand. And in the end, we basically want to calculate, given a segment, how many ways there are to choose 2 numbers from the segment so that their XOR is equal to v. I guess it should be some kind of like traversal. if you understand that all the numbers from the segment are good, what a nasty problem. Okay, let's try to write this. So yeah, I'm doing L minus minus. Let's also do R plus plus so that it's not inclusive. And I will calculate the number of ordered pairs such that P of them, they're from both numbers from the segment, half interval now, and P of them XORs to V. To do that, first let's trim our segment so that it's aligned with force. If v is equal to 0, then it's good to take each number with itself always, and then do the same with the right border. Yep, you want V XOR this. Multiply by 2 because I calculate each pair of different numbers 2 times. So now I will iterate over reminders for first and second modulo 4. Let's look at our table. If it's 0, then it's just n. So if it's 0 or 2, then we have to do XOR n. And if it's 1 or 2, we have to also XOR by 1. So if x is 1 or x is 2, then XOR equal 1. The same for y. So the function solve segment will take the number of elements that I can choose. What I want, and also I should give it the segment. Yeah. Calc on segment should calculate the number of numbers in this half interval for which p is equal to v. I want to iterate over the remainder. Let's first deal with 1 and 3 because it's easier. If v is not 1, then nothing works. Just we'll continue. Otherwise, everything works. Right. the same here, but v should be 0. So here v should be equal to 0 mod 4. And the only number that is good for us is v itself. So if it is on this half interval, then plus equal to 1. And kind of the same here. Yeah. So I'm moving left border to the right until I have this reminder. Then like each fourth number is good for us if L is at least R. So that means that my half interval doesn't have any numbers which are x modulo 4. Otherwise this number of them. This is bad. So now I'm choosing numbers from the segment with some fixed reminders, and I only care about all the bits that are not to lowest, and if to lowest are not 0, then we can't do anything, and the answer is 0 then. Otherwise we can divide everything by 4. So now on this half interval we should choose CNT numbers with XOR equal to V, and 2 minus CNT numbers that are just zeros basically. We should solve 3 cases independently, I think. Here we just choosing 2 zeros. So if v is non-zero, then the answer is 0. Otherwise, this, and we can choose like first number as any of this number, and the second also as any. So that's it. Here I'm choosing one number, the other one is 0, so the number I choose should be equal to v, so v should be on this segment. And this case is the worst one. Here I want to do descent, parallel descent on trig of all numbers, like with lengths up to, I don't know, 60. And if I get to the vertex, I guess both vertices that are either fully inside this half segment or fully outside, I can understand the answer right away. So yeah, doing DFS. I guess I only need like what is my height? And these numbers, sure. Yeah, there should be different for two different vertices. This is amazing. Yeah, if this happens, then I can choose any number as the first one, but the second one will be uniquely determined, but it's okay. So just return X. Otherwise, I can iterate over two possibilities for the next bit. In the first number, using V uniquely determine what is the first number, what is this bit in the second number, and make the transition. Of course it doesn't work. Why would it? Yeah. amazing. So in this case, after this we will get 0, 4, so this doesn't happen at all, but then this happens. And I want to get 3, so like using these numbers I want to get 3. This is done in 4 ways, that's true. Okay, let's say this. Oh, right, I do not return anything here. Should sum up all the values returned and then return this. Okay. That's a lot. So I'm saying that 0, 0 is good. That's insane. I should return 0 here right away. It's 3, but I return 1 somehow. Solve second. 2, 3. Oh, if it's not 0, then return 0. And now it's always 0. Oh, right. If x is 2, then I need to XOR by 3. Problem might be here. Let's check it somehow. Yeah, it's still not correct. It is correct here, but not here. 0, so maybe this is wrong. Yeah, why am I doing -1 here? That's still not right. Oh, right, because I have changed them. Okay. And it's still wrong here. That's not right. Should be 4 here, because let's check. R should be 12 and 20. Yes. Oh no, yeah, that is correct. This is not correct. Should call solve segment 0, 0, 12, 20. and do this, and do this. If it's non-zero, then it's zero. Come on. So many stupid mistakes. It would be a miracle if it works. Okay, it's a miracle. There should be a simpler solution, I guess. What? In problem E, we consider the following process. So we are working with numbers between 1 and v. We start with value a, and we also have this arrays of lengths n and m, of numbers from 1 to m, and then we doing n times m operations, like basically we write down its infinite repetitions, and then n times m times we run through this infinite string, and replace our current value with median of our current value and two numbers in like one number from the first segment sequence and one number from the second sequence. Then we are given only lengths of these sequences and like maximum value we're working with and our starting value. Then we try all the possibilities for the sequences, and we want to find the sum of the results. Then what? Well, when we are working with medians, it's usually a good idea to do kind of binary search, or like split the segment of all possible values in two parts, like small and big, and basically replace all small numbers with zeros and all big numbers with ones. And then like run the same procedure. What's the point of that? Well, the median works the same. So we can either first take median, then do this replacement to zeros and ones, or we can first do replacement for zeros and ones and then take median. So if we fix some number x and say that all numbers that are smaller than x are zeros, and all numbers that are bigger or equal than x are ones, then we will get 1 in the end. On if and only if the actual result is bigger or equal than x. We need to find the sum of all answers, which is equal to the sum of this thing if we also iterate over x in the beginning. Well, because each number gives contribution which is equal to the number number of numbers that are less or equal than it. And now we are working with sequences of zeros and ones. There are like different number of ways to get them. But okay, so we fix x from 1 to v. Numbers that are smaller than x are zeros, and numbers that are greater than or equal than x are ones. So this count of these numbers is x minus 1, count of these numbers is v minus x plus 1. So our initial value big A will just be something. And we are now constructing sequences of zeros and ones, but each zero can be like actually was one of x minus 1 numbers that are smaller than x, and each one of ones was actually one of v minus x plus 1 numbers that are greater or equal than x. What are the transitions? Like what happens when we do this now? If these two numbers are not equal, like one of them is 0 and the other one is 1, then our number doesn't change. Otherwise, our number becomes the same as this. Like if both of them 0, then median is 0. If both of them are 1, the median is 1. So we want to find what was the last time the elements were equal and what were they equal to. N and M are not very big. We can try to iterate something. Like we are interested in the last time when two elements are equal. So let's iterate over pairs that we will compare from the end. How will that work? The last one is n's and m's. If they're equal, then whatever happens next, like everything is the same. If they're not equal, then we can draw an edge between n's and m's element and say that they should be different. Then like n minus 1, m minus 1. We are going backwards. Each time we should consider the possibility, what if they are equal? And do something. It's not very clear what, but something. What happens when we, let's say that n is smaller than m, we'll reach 1 m minus n plus 1, say that they're different, and then we jump to n again, and here we have m minus n, and we say that they're not equal. So we are building this graph. It is bipartite already, and well, it's possible to make everything not equal. Just make all the first sequence to be zeros and the second sequence to be all ones. maybe we have to somehow use that we're only interested in sum. Like if after some edges I stop and say that okay, these two values are equal, and then the answer is equal to these values, that means that the answer doesn't depend on starting value. But then if I randomize, well, yeah, we are trying all the sequences and taking a sum, we can say that we randomize each element independently, probably, and take expected value and then multiply by something like v to the power of n plus m. If I also randomize the first value, then the answer surely, like the expected value should be 1 plus v over 2, because like everything is symmetrical. And the only difference between random first value and fixed first value in the cases where I don't stop, so everything is like all the edges are drawn. So we can like start with answer for randomized starting value, and then add the difference between this situation and randomized starting value. Answer for randomized starting value is v plus 1 over 2, and the difference will only be seen when all the edges are drawn, and this case is somewhat easy. Like we, if all the edges are drawn, we just group the numbers by remainder GCD and M. Different vertices with different reminders cannot be connected. Vertices with equal reminders surely will be connected. So we actually have GCD and M full bipartite graphs on n divided by GCD and M vertices in first part, and M divided by GCD and M vertices in the second part, and we should color them so that it's bipartite. So we either color in each component separately, we either color all of these zeros and all of these ones, or vice versa. So in each component the answer is basically, well, x minus 1 divided by v to the power of n divided by GCD multiplied by v minus x plus 1 divided by v in power of m divided by GCD, plus the same thing but swap the components. And we do this for each component independently, so to the power of GCD. So that's the probability that a randomly colored graph is like will be actually bipartite with this coloring. And that is the difference between random with this probability for this given x, the answer will depend on starting value of a. So we will add starting value of a minus 1/2, because like expected starting value of a if it's random is not 1/2. So it's like a minus x minus 1. No. If it's random, then the expected value is v minus x plus 1 divided by v. So we multiply this by this thing and add to the answer. That's it. And I can calculate that just by iterating over x and summing up this thing. Okay, let's try it. I said that I iterate over x from 1 to v. Instead I will iterate over like x minus 1, so that there are no this plus ones, minus ones. So mean probability that everything as we wanted. We need to calculate GCD. Probability that in one component everything is good is p to the power of n multiplied by 1 minus, let's call it 1 minus p is q. Then it's q to the power m plus p to the power m multiplied by q to the power n, and then to the power of number of components, which is GCD. Our value is it true that a is strictly greater than x? And we should subtract the expected value, which is q. And to ans add value times probability, and now multiply ans by v to the power of n plus m, but I have divided them by GCD, multiply back. Okay, looks like it works. Are there samples with GCD not equal to 1? Okay, it works. Cool. Well, I don't have time to solve problem F, but let's read it. Okay, so problem F is about some gambling stuff, like we can have from 0 to n inclusive integer amount of money. For each value we are given a starting probability, and then k times we will gamble, and if we have x money, then with probability x divided by n, x is decreased by 1, with probability 1 minus x divided by n, it is increased by 1. We are doing k such operations, and we want to find the final vector of probabilities. And k is very big, n is reasonably big. Well, then we have some starting distribution, and multiplied by some fixed matrix k times. Can be seen like we have n toggles, like n lamps. Some of them are on, and each time we choose the random one equiprobably and switch it. And we are interested in number of lamps switched on in the end. Not sure it gives anything. Well, I kind of don't believe that I will get any great ideas in 8 minutes. So we can wrap this up. Well, I did better than the last time, so that's good. And yeah, the last problems are hard, it seems, not only for me. My solution to problem E is beautiful. My solution to problem D is awful. So that's balanced. Okay, thanks for watching.